Hello students, today we will discuss another interesting topic called as an HDL language. HDL means it is a hardware description language. So in previous years there is an interesting development in case of digital system where we can do a textual type of discussion for the logic circuit that we have studied in the previous class. So particularly in previous class we have studied some basic circuits, basic logic gates, AND gate, NOT gate and an OR gate, as well as we have studied universal gates like NAND and NOR gates. By interconnecting those logical gates, you can implement a higher digital circuitries. So today we will see what is an hardware description language which supports a textual type of description for the functionality of different basic gates as well as for higher circuits also. The major advantage of using an HDL language is, this language can be utilized to describe any complex circuitries in a simple manner. The another advantage of this hardware description language is this software, or I can say the software which we use to describe the language, describe the behavior of a digital circuit, will support to write a test bench which will be used to generate and testing waveforms which can be given to a model that you are written to see whether the functionality is working correctly or not with respect to the model that you are written it. And as well it supports a synthesis, synthesis in the sense whatever the program that you are written should be converted into a gate level language to see how the circuit is formed for the language that you are written in describing the digital circuit. See, nowadays in industries majorly the digital circuits are designed by using hardware description language so that you can implement the digital circuits in a faster way. That means you can describe the hardware with a faster rate. See, in HDL languages we have two types of language, particularly one is an VHDL, another is called a Verilog VHDL, the another one is a Verilog language Verilog HDL. VHDL, this is an acronym actually, very high speed integrated circuit hardware description language. Another one is called as an Verilog HDL, that is Verilog is nothing but a verification language. See, the features in VHDL and Verilog HDL are common, but the most preferably used is a Verilog HDL. So VHDL is more documentation type and Verilog is almost like a traditional language that you have studied in previous semesters or something like C language But there is a difference between something like an HDL language that we use to describe a digital circuit to the traditional language that we use in C programming, the traditional languages that we use in computers The major difference that we can see between a traditional language to an HDL language is, in traditional language like C, the execution of instruction is in sequential order. But whereas in case of an HDL language, all the instructions will execute in concurrent fashion. That is the major difference that we can see between an HDL language and traditional languages like C, because the hardware, in practical sense, the hardware will execute concurrently or parallelly or simultaneously. That's why that feature is required in case of an HDL language to describe any type of digital circuitries. So another advantage that we have in terms of description language HDL is it supports the different level of description in terms of digital circuitry. Particularly, we have three levels of description or coding style. One is called as behavioral coding. The second one is called as data flow coding. The third one is called as structural coding or component level coding. Structural coding or component level coding. Depending upon the availability of the information which you wanted to describe in terms of language, we can utilize any of this type of coding. So particularly in behavioral coding, we don't need to have a circuitry or the Boolean X type of expression to describe describe in terms of language. If you know what is the input that you will be giving, if you know what is the output that you have to get, it means usually by using the sequential type of statements, you can describe the functionality of the digital circuit. That is an advantage. In case of data flow coding, by identifying the truth table with respect to the design that you wanted to design, so you can use the logical expressions to define in terms of language, that is called as a data flow coding. If you have a circuit diagram with respect to the logical expression, means you can write a coding in terms of the by specifying the components within the program itself. That is called as a structural coding. Depending upon how the circuit diagram is formed, in the same way you can mention the components in your programming itself. That is called as a structural coding. So each is having an advantage as well as disadvantage in terms of representing the information or a digital circuitry in terms of language. Like depending upon the usage, depending upon the requirement, either of these coding techniques can be utilized. So next we will see how to write a Verilog code and a VHDL code for a simple model. Then I'll try to correlate what is the traditional method that we were using to represent any programming language in terms of VHDL as well as in terms of Verilog programming. So in traditional sense, particularly in laboratory, what we do is we will select an IC and then we will try to interconnect a wire and we will try to see what is the output that you will be getting it like. So usually we will be selecting an IC means, see IC will be having a label like 7432 or something like this, and for this you will be having an input pins as well as an output pins like. See, this we call it as a black box, for which you have the number of inputs as well as number of outputs depending upon the requirement, and we will be giving the label to identify what type of IC it is like. So technically we call for this as a symbol like. So inside the symbol we will be having a circuitry which tells how this symbol is working, for which we call it as a schematic like. Schema of interconnecting the logical gates to get the required output is nothing but a schematic. Okay, so internally this IC will be having a digital circuit interconnection which specifies the behavior of the symbol. Like this is just a traditional representation of any hardware circuit. So this I will try to convert into a VHDL language. Like. See, the symbol in case of language representation is called as an entity. Symbol is nothing but a keyword here in terms of an HDL representation. Entity is nothing but a symbol in terms of traditional representation. Entity, as I said before, the symbol is having a label. So particularly I will take this label with respect to this symbol as an OR gate or something like that. OR gate is the entity name. So this entity name ends with another syntax called as is. So next you have to define the ports with respect to this entity. So depending upon how many number of inputs it is having, suppose say I'll take it as an AB as an input and output is nothing but an Y here like. So we will be calling these input pins are nothing but a ports. So port, we have a key word called as port here, and you have to mention which are nothing but an input ports and which are nothing but an input output ports. For this I'll try to write something like AB. A and B are nothing but an input port. See, we have mode of the ports here like whether these are nothing but an input pins means we have something called as syntax is in. In is a syntax, and the type of the data this will take as an input is nothing but a standard logic. So if I mention it as a standard logic means we can give an input like 1, 0, Z and a don't care condition. Again one more output terminal is there, output port is there, that is Y. You have to mention what is the type of that port, it is an output port, and what is the type of output that it gives is standard logic, the same type of output it gives like. See, for the last syntax you should not put a semicolon, you have to put a closing bracket and you have to put a semicolon here like. See, this ends the description of an entity. Say VHDL model particularly consists of an entity and an architectural description like. So this is just an that is whatever we can see outside in terms of an AC, that is represented in terms of an entity here like entity name is having the ports like A and B are nothing but an input ports and Y is nothing but an output port here like. So end OR gate, end is a syntax here, entity is a syntax and port is a syntax like. A and B are nothing but an user defined labels, and in out is also nothing but a syntax as in represents the input ports and out represent an output port for this gate. So next, as I said, the schematic means it is a schema of interconnection of the components and which specifies the functionality of this symbol or an entity. So in case of VHDL we call this as an architecture like. Architecture as a schematic in traditional sense we call it as a schematic. In terms of an HDL language we call it as an architecture, is nothing but a syntax like. So in VHDL, as I said, in case of an HDL language, we can do three type of descriptions. Like one is called as a behavioral type of description, another is a structural description, the third one is called as a data flow description. To differentiate, so we should give an architecture name, that is OR gate architecture. I will try to write it like this: OR gate architecture. Of what, for what entity you are writing this architecture means you have to specify the entity name here. This is entity is nothing but an OR gate. Is a keyword there. Architecture name of an entity is. So you have a declarative part here, like, see, we will see in detail in the later classes. Just I am writing how the HDL language can be written for a simple OR gate. Then we will try to see what all the different features are there and how best you can utilize to represent for a bigger circuitries. Like, see, after writing this line, next you will be having a begin. So next what you have to do is you have to write a concurrent type of statements. Like concurrent type of statements in the sense I have to define the functionality of this entity. So what I do is, as I said, we have something called as y as an output port. We will be having something like less than or equal to means it is an assignment symbol. It is not a logical type of operator. It is less than or equal to, and we have an input a, and so we have a syntax called as an OR. It is predefined type of syntax we have in library, which can be utilized to do an operation of OR gate, and the another input that I will be having is B. So I will put a semicolon because this is an end of the statement. Like, so next statement that we will be having is end architecture. End architecture name you have to put it like end architecture. So this is a simple end will be begin and end will be there, like, okay. So begin and end, this is a syntax. So end of architecture name you have to write it like. So in a VHDL model we have two parts here. One is called as an entity, another is called as an architecture. Entity defines the outer view of your model, and architecture defines the functionality of an entity. This is a simple VHDL model for an OR gate. Like, see, what we do is we will be writing a test bench to check whether the functionality of this will give you a correct output or not. Like, see, that test bench will tell you later how to write it. Like, now we will see how to write a Verilog model for the same OR gate. Verilog model. See, in Verilog we don't have something like an entity and an architecture. Everything is defined in a model itself. We have a keyword called as a model, Verilog model for OR gate. OR gate representation, OR gate here. See, as I said before, in case of Verilog, we don't have separate entity part as well as an architecture part. Everything is defined in the syntax called as model itself. Model is a keyword here. The name of the model you have to specify. Just I'll try to give it as an OR gate. Like, the model name is an OR gate, and you have to specify what all the inputs that the gate is having it. So OR gate means I have taken A and B are nothing but an inputs here, and Y is an output. You have to put a semicolon there. Like, okay. So next you have to define explicitly in these arguments which are input and which are output. That's why you have to write input is a keyword. Input is a keyword. So I have to mention what all the input ports here. A and B are nothing but an input ports, and output is nothing but Y here. This is just a declaration of the ports that you have taken in terms of an OR gate. Input is A and B, output is Y. So the next you will not be having any separate syntax for describing the functionality. Directly you can write in syntax here, like syntax which describes the functionality of an OR gate. For that we have something called as an assign. So Y is equal to, we have some logical operators with respect to OR gate. So that is logical operator with respect to OR gate is nothing but a pipe. So if I write like this means automatically it gives an output is equal to OR gate output. So next the statement that we will be using is model, end model. See, the semicolons are written with respect to this, but end model will not be having any semicolon. This is the simple textual type of description for an OR gate in Verilog. So now in industry, most of the industries will use a Verilog description because it is very similar to something like C program. That's why most of the designs are done logical expression, logical programming is done in terms of Verilog models. Okay. So next we will see how to check this. Like, see, in market there are many vendors with respect to software which supports to write this type of description. Particularly the example is Xilinx, Cadence, Synopsys, many are there, but in colleges we preferably use Xilinx software, in which it will support to enter the language, that is HDL language, to describe any type of digital circuitries, maybe in terms of an VHDL and Verilog. So by using that software, there are two ways of simulating it. Like, two ways of simulating it. One is by writing the test bench, another is by using the simulation software that is available with a software that you are using it. Like, that is particularly in Xilinx, you have Xilinx iSim, like, which will support to do the simulation with respect to the model that you are written it. Like, okay. So there are two ways of using it. Like, one is by using an iSim, you can force the value to these ports A and B, and you can check out what is the output that you are getting for a particular duration. Like, that is one way of doing it. Another way is you can write the test bench for simulating. The meaning of test bench is you will be creating an environment, or you will be writing a model programming model by which we can generate a software waveforms. Those waveforms can be given as an input to the Verilog model to check whether it is working correctly or not. Like, so this is your testing model, that the program that you are written it, and you will be creating a test bench. This is called as test bench, which generates a waveforms or the inputs which can be given to the model that you are written, and you can check out the output what you are getting it. Like, okay, this is your model that you are written it. Like, and you can check the what output that you are getting it. Let us see how we can write a test bench with respect to an OR gate, and what are the things which we need to define in case of test bench to simulate it, whether it is giving a correct output or not. Like, so as I said before, the advantage of this description is, if you are not getting a proper output, means you can go back to the program, you change the instructions such that you will be getting a correct output. Like, okay. See, the program that you have written, that I have written in terms of an OR gate, is called as a data flow coding. There is another way of writing it. Just I will try to write in terms of a gate level coding or a structural coding for an OR gate itself in terms of an Verilog, because according to the prescribed book in the syllabus, he majorly uses an Verilog rather than VHDL program. Like, so that's why I will try to write the description for an OR gate in all the description levels, and I will tell you how to write a test bench for simulating those models. The first model that I have written for an OR gate is in data flow type of coding. Now, what I do is I will try to write a structural coding with respect to OR gate by using a Verilog type of coding here. So as I said before, you will be having a syntax called as a model, under which you will be writing a textual type of description for an OR gate. Again, I will try to put OR gate is the name of the model, and it is having an input says something like A and B, and output is nothing but an Y. See, Verilog is case sensitive. While referring with respect to the names, or while using the inputs and outputs in terms of functionality description, the same letter case should be there. Like, if you use a small case, means it will not identify, it will give a mismatch or something like that. So now you have to define the inputs here. Input is a keyword, and the inputs according to my OR gate model is A and B are nothing but an inputs here, and the output is Y. Output is Y. Now what I do is I will write the functionality here. So you can see here in my slide also, inputs are A and B, it defines the two input port, output is nothing but an output Y is nothing but an output port here. Like, see, now here I am using an R as a component itself. Like, R is nothing but a component which is predefined, like in case of library, that we can utilize it. See, R is a syntax in case of an VHDL program, but here R is nothing but a predefined gate which is already there in the library, that we can use it directly. Or otherwise, what I need to do is I have to write one more program for an OR gate, then you try to utilize this component while describing in terms of structural coding. Okay, so now as I said, we have an OR gate in my library. See, to differentiate, if the same OR gate used many times, means I have to label it to differentiate in which instance that is being used. Like, that's why I'll give something like G1 is nothing but a label. In that instance, I'm using an OR component. Like, so then you have to map these ports of this component to your model that you are implementing it like. So how do you map it? Means the Y is nothing but an output port that you have to write it first, and then A and B. You can map with the same labels like. You can map with same labels here. So R is nothing but a component that I am specifying in my program, in my Verilog model, which works like an OR gate like. So G1 is nothing but an instance. You put a semicolon here. Next is a end model. This type of coding is called as a structural coding. Structural coding. So depending upon the component that you specify in the circuit, same components names that you can mention in the programming model itself. That is called as a structural coding. So this gives the clarity in terms of how the circuit is framed for a given logical expression according to your requirement. Like this is end model. So next we have another type of coding called as behavioral coding. In terms of an OR gate, I will try to write it. See, up to this level the model description is same, OR gate, and it is having an input is A and B and output is also Y. So the difference with respect to behavioral coding is we define one more object called as a register. In that we will be holding the data temporarily. So whenever you do a behavioral coding, means naturally we will be using a sequential type of statements in that coding. That's why so it is necessary to use an object called as a register with respect to an output here. Next, as I said before, we cannot put a sequential statements directly into a Verilog body. As I said before, the body of a model should contain only the concurrent type of coding. You cannot write a sequential type of statements, because sequential type of statements will execute sequentially rather than parallelly. That is not allowed in case of programming with respect to an HDL type of description like. That's why we have one syntax called as an always. Always is nothing but a syntax which will support me to write the sequential type of statements in an HDL modeling. So we have a syntax called as at the rate of. Always is a keyword. At the rate we have to mention the sensitivity least with respect to always. Sensitivity least in the sense something will change on the inputs here, that is A and B, or nothing but a sensitivity least. In some books they will write it as A or B. If anything is changing on A and B, means A or B, means naturally this always statement will execute, otherwise it will not execute like. So A or B. So once I use an always statement, means next you have to use the sequential statement like if. So we will see what all the sequential type of statements are there in the next chapters, like depending upon the model complexity of the model increases. So now just I will try to utilize the sequential statement called as an if here. See, in this case I will try to write something like if A is equal to, see, if I am writing something like a sequential type of coding here, that is a behavioral coding, means I should have something like the truth table representation, that is with respect to an OR gate. When I give an input is equal to 0, 0 means the output should be equal to 0, and 0, 1 means the output is equal to 1, 1, 0 means 1, 1. When it is equal to 1 means the output is equal to 1. So sequentially I check for all these inputs and to whether the output is equal to 0, 1, 1 or not like. So if A is equal to 0, okay, and if A is equal to 0 and B is equal to 0, my output should be equal to 0, that is Y is equal to 0. So that way you can assign it like Y is equal to 0. Else if, see, otherwise we can check the values. A is equal to 0 and B is equal to 1 means Y is equal to 1. So you have to check for all the input status here, and that is input values, and you have to find out what is the output value. In the last you can write end model. If and end you can write it if it is required to check the multiple assignments, otherwise you can close it like. So end model you can write. This is a behavioral description in terms of an OR gate like. You know what all the input values that you are giving it, and if you know what is the output that you are getting, it means naturally you can describe by using a sequential type of statement. One thing you should remember is always is a statement which allows me to write the sequential statement within a model, otherwise you cannot write it like. This is a simple a behavioral description like. So depending upon your information which is available in case of designing, you can describe a different levels of representations like. So this is more advantageous if you don't have any information regarding with respect to a logical expressions or the circuit diagram is directly you can implement by using a behavioral coding like. If you have a logical expression which is of simplified type means directly you can go for a data flow coding type. If you have a circuit diagram is basic, so you can write at a structural coding like, or you can code in terms of structural description like. Okay, so now we will see. After writing this in a software, what we do is we will check the syntaxes, whether the syntaxes that I have written are correct or not. Like if the syntaxes are not correct means naturally you cannot simulate it because it shows some syntactical errors. Then what you have to do is you have to check the syntax and you have to correct it. Then you have to go for simulation by either by using a simulation tool directly which supports a waveform type of entry. In that, by forcing a values to inputs and you can see what is the output in terms of a waveform like. Otherwise, rather than forcing the values directly by using an wizard or something like waveform, you can write the test bench and that test bench can be linked to your model. Automatically that test bench will generate the input waveforms that will be given to the model that you are written it, and you can see the output from that, the ports that you are defined in case of a model like. So next we will see how to write a test bench. Just I am showing the test bench model for an OR gate here, which we are written in terms of different type of coding there like. See, this testing model will be having the model with which gate that you wanted to check. That means this test bench model will be having a name called as test R. Okay, so then you have to define the register called as A and B, which is nothing but a data object which holds the data temporarily. That is output of the input data which holds temporarily, which is generated by this model, and wire X is nothing but an output port on which depending upon the inputs that you will get, the value will change, that will be temporarily hold on the wire here like. So OR gate, so which gate that you are simulating it means that is a OR gate. This is a label that you are given here like organization, and we have a next syntax called as an initial. This will tell to simulate the sequential type of testing will begin, that is called a start simulation like. It is particularly used for always statement to initialize the simulation process like. Next you will be having a begin to generate the different type of inputs which can be given to a testing model. Then A, and as we know with respect to an OR gate we have an input like A and B. A and B here, A and B, that is one type mark B0. 1 represents the number of bits that you will be giving to an A, and B is nothing but a binary, the value is nothing but 0 here like. Signifies a binary digit with a value is equal to 0. And B I am giving the length of the binary is 0, that is 1 bit, 1 type mark, B is nothing but a binary, the value that I am giving is 0. So now the AB is assigned with 0 0. So it will simulate with respect to this value for 20 seconds delayed like. The next input that I can give it after 20 nanoseconds is, see this here I am using an hash mark which will be used to delay, to generate a waveforms with that much delay, that is 20 nanoseconds here like. So another input that I am giving is 0 1. The next input that I am giving is 1 0 and 1 1 that is given here like, and 20 nanoseconds delay will be there in giving the inputs to that testing model to check the what is the output that you are getting it like. End model. This is the test bench like. In software automatically this will be generated. If you want to change the values of the input to check whether your model gives the correct output or not means just you can change the values here and you can check it for any other models like. So once you write the programming model means there is an facility in feature is there in case of a software. If you press the test bench creation and you mention the input ports and output ports means automatically this model will come. In that you have to give a different inputs for in the test, you have to mention the different inputs in the test bench so that it will be used to check the model that you are written it like. Model that you are written it. Okay, this is test bench like that you can create a test bench for any model that you have written in terms of Verilog or VHDL, and you can simulate to check the functionality with respect to the model that you have written. If anything is wrong, means go back to the program, change the syntax or instruction and correct it, and again re-simulate it by using this test bench model to check whether you are getting a proper output or not. Okay. So next what we do is, see, the next we will study the combinational logic circuit. I hope the students, you got an idea like what is a text type of description in terms of various a simple OR gate. The same thing can be repeated to write for another logic gates like AND gate, OR gate and an AND gate. You can write a simple models. Later when you go for a higher type of description, for all those digital circuits you can write an Verilog model or a VHDL model and as well you'll be giving an exposure to higher syntaxes that we have in case of Verilog model or maybe in terms of VHDL. See, switching between VHDL to Verilog is quite simple. So preferably in all the books they will write in terms of Verilog. That's why in all discussions we will be writing a Verilog model for the model that we discuss in terms of digital circuits. Okay. I hope you have understood how to write an textual type of description for the simple logic gates. So just I'll try to summarize in terms of a Verilog model and a VHDL model. VHDL model will be having an entity and an architecture. In entity, just we describes what all the type of input ports and an output ports are there, and by mentioning the label to an entity, and in architecture we try to define the functionality of that entity. But in case of Verilog model, you will not be having an explicit two parts to describe an input port as well as functionality. You will be having a single definition or the syntax called as a model. In that we will be specifying or we will be declaring the inputs and outputs as well as the functionality within the same model, and it will be having an end model which specifies the description is overlay. Okay. So another one is in HDL language we can do the different type of description. One is called as a behavioral type of description, another one is called as a data flow type of description, the third one is called as structural description. Depending upon the information availability, you can code in either of these styles. So the next topic that we will see is combinational logic circuits. So in this combinational logical circuit, just we will be studying the Boolean algebra. We will be studying Boolean algebra as well as the simplification methods, simplification techniques, or I can say. So what we do in the beginning is we will try to discuss the basic laws and as well as De Morgan's theorems in terms of Boolean equations, and then we will try to simplify the simple equations in terms of combinational logic circuits, and then we go for something like the representation in terms of SOP or a POS, and then we will see how do you simplify that circuit in this session in this combinational circuits. See, first we will try to see what is the basic laws in terms of Boolean algebra and the theorems that we use in terms of simplifying the logical expression. Simplifying the logical expressions. See, first we will see or we will discuss the basic laws in terms of Boolean equations. See, we have basic three laws here. One is a commutative law. The second one is called as an associative law, and third one is called as distributive law. So first one we will see what is a commutative law, that is in terms of an equation is A plus B is equal to B plus A, that is commutative property or a commutative law, and B is equal to BA. See, A and B are nothing but a logical variables. Why we say it is a logical variables means these labels can take either 1 or 0. What is the significance of this commutative law? Means the order of the logical operations are not important here, like it is unimportant with respect to the logical operations A plus B or B plus A. Finally the output that I will be getting is same. See, in logical circuit sense, this commutative law will help us to transpose the input such that you will be getting same output here. So the another law is nothing but an associative law, that is A plus the bracket A plus bracket B plus C is equal to A plus B bracket plus C. Another one in terms of product terms is A of B C can also be written as something like AB also. This indicates, this associative law indicates combining of variables has no effect on the final answer. Either you can group B plus C, or if I group A plus B means it gives the same output, like it is not having any effect in terms of final answer. Here also it is something like A of B C or AB of C means it will give the same type of output like. Okay, the third one is nothing but a distributive law. It is more of algebraic type of expression here, like algebraic type of algebraic equations that you can do here. It is a simple one. It shows the logic equivalence and give a simpler logic circuit type of representation. Like here, the B plus B, that is operation will be changed here. Like here it is a product, here it is something like plus operation. It can change an equivalence. Like if it is an product term is there means that can be converted into an SOP, that is POS also, or POS is converted into SOP form. That is the distributive advantage of distributive law. So next, these are the basic laws that will be having an advantage in terms of implementations or simplification of logical equations. Like so, next we will see the Boolean operations in terms of an OR operation and AND operations. As well, we will try to discuss some of the theorems which are very much required for simplifying the Boolean equations into a simpler form, so that I can implement by using a minimum number of gates. So the first one is the Boolean relation we will try to see in terms of an OR operation. That is, see, OR operation means, as we have seen in the previous cases, like there will be two inputs for an OR gate and the output is equal to 1. So the operation is, when I say that is y is equal to a plus b, is a logical expression for an OR gate here. So when I give, if I take a plus b, just we'll try to see what is the relation that exists. If I give 1 plus 1 means it is equal to 1. 0 plus 0 with respect to this means it is equal to 0. Here the plus means I am not using a decimal type of addition here, like it is nothing but a logical operation that I am, or operation that I am doing it, like 1 plus 1 is equal to 1. See, similarly we will try to verify with respect to one variable, if I add another value like 1 and 0 means what will happen. That is operation with respect to Boolean expression. Like the first one is, suppose say a is there, if I add 0 with respect to this, like what is the output that I will be getting in terms of Boolean operation equation is a plus 0 is nothing but a. So if I add with 1 means, that is a logical operation with 1 means it is equal to 1. A plus 1 is equal to 1. So if I give the same type of a plus a, that is a plus a means it is equal to a here. See, that is, for example, if a is equal to 1 means 1 plus 1 is equal to a, that is 1 itself. What is the value that I have substituted for logical variable here is 1. So that means you will be getting the same value, that is a. Next is a complement one, like a plus a complement. So what is the value that you will be getting? A plus a complement means it is equal to 1. For example, if I substitute a is equal to 0 here, 0 plus 0 complement, 0 plus 0 complement is 1. So what is the output that you are getting? This is an 1, like. So a plus a bar is equal to 1. This is the relation, Boolean relation with respect to an OR operation. Similarly, we try to see what will happen with respect to an AND operation, like AND operation. So a dot 0, the first one that I will take is, say a dot, this is an AND operation, dot represents an AND operation, a dot 0. So a dot 0 means the output will be equal to 0 itself. Like, see, if I do an AND operation with a variable and a 1 means a into 1 is nothing but a that you will be getting it, like. So another one is, we have another one, a dot a, same logical variable means I will be getting a. See, another one we have in terms of operation is a complement, a dot a complement means the output is nothing but 0. If I multiply the complement number means I will be getting 0. Okay. See, these are the operations with respect to a Boolean equations, like Boolean representation or equation. We will see some of the laws, particularly De Morgan's theorem, that is theorems, that is De Morgan's theorem and duality theorem, which are very helpful to simplify the logical expressions into a simpler form so that I can implement easily in terms of digital circuits. That is, De Morgan's theorem is, suppose I will try to write AB whole bar. The theorem, De Morgan's theorem, is equal to A bar plus B bar. This is De Morgan's theorem in terms of product of variables. So another theorem that we have is A plus B whole bar. A plus B whole bar means this is A bar into B bar. This is a De Morgan's theorem. So another one we have is, if I double complement the variable, means the output will be equal to, that is equal to A itself. This is a De Morgan's theorem, which will be useful to simplify the logical expressions. So we have a duality theorem. The another theorem that we have is a duality theorem that will be helpful in converting an AND operation into an OR operation, like OR. Otherwise, OR operation can also be converted into AND operation, like that is A plus 0 is nothing but A, and A dot 1 is equal to something like A. This is a duality operation. So duality operation, which will help me to convert into another form so that it can be implemented, or the digital circuit can be realized in a simple way. Okay. See, another theorems that we have is A plus A bar B. This is equal to A plus B. A plus B, A bar B is equal to A plus B. So these are these operations, or I can say the laws that we will be using, our theorems, will be helpful in case of simplifying the logical expressions. So just what I do is I will take up some of the examples of logical Boolean equations, and we will see by using these how we can simplify it, like how we can simplify this. Say I will take a first example. Let us see how we can simplify this. That is, the first one is y is equal to AB bar plus AB. This we need to simplify it, like. So simplify in the sense, AB, you try to find out the two product terms by which you can take a common factor, so that that common factor will correlate to any of the theorems and the laws that you have studied here, like, or the operation that you have studied in terms of Boolean equation. Here I can take A as a common factor here. So B plus B bar, it will become like B plus B bar. According to the equation that we have written previously, B plus B bar or A plus A bar is equal to 1. So the simplified form of this logical expression is nothing but A itself, so that you can reduce the number of terms. Okay. Suppose if I implement the same thing in terms of digital circuit by using an AND OR operation, means I will try to write like this. Suppose say this is my AND gate for implementing this A B bar A here. This is one term I will be getting AB bar. So another AND gate I will try to use it, for which I will give an input is equal to A and B, and I will be getting an output is AB. So next, to do an OR operation, I will try to connect an OR gate. I will connect an OR gate so that you will be getting AB bar plus AB. This is a total circuit, that is AND OR type of circuit for this given expression here. Okay. So next, the another, after taking a common factor, how we can implement it means, so I have to use an OR gate here, B bar. So you will be getting, this is B plus B bar. I can connect it to an AND gate. This is on one input, another is an AND gate that I have to use it, and I will get an output for this level, for this implementation. See, if I simplify it by using the theorem B plus B bar is equal to 1, means I will be getting A. See, you don't require any gates to implement this. Just if I connect a wire between A to Y, means you will be getting an output here, like. That means by simplifying the Boolean equations to a simpler level, I can reduce the number of gates that are required. That means I can use a minimum number of gates to realize this or implement this logical expression, so that the cost as well as it is more reliable to implement it also. That means the output will not change if I operate it many times. That is called as a reliability. Okay. So we will see some more examples how to simplify by using these theorems and laws to put a Boolean equations into a simpler form. The second one that I will take is a little bit a complex equation. Later I will take it like the first. We will try to see how we can simplify this like a bar b a and a plus b. This is again a simple equation that I have taken to simplify this by using any of these theorems. So a bar plus b and a plus b. So now what I do is multiply these terms a into a bar. To simplify that, just multiply a bar with an a and a bar b. Next is a and b plus b into b. Just I am doing a product term here. So according to the last, like a dot a bar means it is equal to 0 plus a bar b plus a b. If b into b means it is the same term, that is I will be getting that is equal to b itself. Okay. So now what I can do is I can take a common factor here. I can take a common factor like b. This is equal to a plus a bar into b plus b is there, like as I know already, like a plus a bar means it is equal to 1, that is b you will be getting, and this is equal to plus b. So b plus b means it is again equal to b. The simplified form is b itself. So that is this is how we can simplify the bigger terms Boolean equation into a simpler forms by using this type of theorems and an operations with respect to Boolean equations. So I will take one more equation, that is a bigger equation. Let us see how we can simplify it. How we can simplify it. Next is y is equal to a bar b bar c bar plus a bar b c bar plus a b bar c bar plus a b c bar. Students, try to simplify this like. Now how do you simplify this expression? Means you have to find out the two product terms which are having a common. Okay. So which are having a common terms here, like see after taking the common I will get any one of the law or the theorem that you studied before, like. See in this case AC bar is common with respect to these two terms. I can take AC bar as a common factor, b plus b bar you will be getting. In this case a bar and c bar I can take it as a common factor, so b plus b bar. So b plus b bar is nothing but a 1, so I will be getting a bar c bar. Here b plus b bar is nothing but again 1, so I will be getting ac bar. See from this also you can take a common factor, that is equal to c bar. I will be getting a plus a bar. So what is the final answer? You will be getting y is equal to c. This is called as simplification of the bigger Boolean expression to this level. It will become very simpler. Okay. The last one that we will see is that is a little bit bigger equation, but the simplification is quite easy. So like that. Many problems are given in the textbook, like you try to go and solve those expression. By that we can remember these equations and the theorems in an easy way, such that you can simplify any bigger equation into a simpler equation and you can realize the circuit in a simple way. Okay. So friends, I will try to summarize what are the things which you have studied, like. So we have studied something called as an HDL language, which is very helpful to describe the digital circuitry in terms of a textual type of description, which is very helpful. That means the designing can be entered with a minimum time into a software, so that you can simulate and check what is the output that you will be getting it, like. As well, the HDL language will support for a simulation. That is very advantageous. If you are not getting a proper output, means you can go back to the program, change it, and until you get a correct output, like. As well, this software, the HDL language will support for a synthesis, like that means the software which we are using to write a description in terms of language will support a synthesis which will convert the English level language that you have written in terms of programming to an hardware structure also, that is gate level coding, to verify how the circuit is formed, like to check whether you get the correct output or not. Like so in SDL description we have studied something like three type of description levels. One is a behavioral, data flow, and third is called as a structural description. Depending upon the availability in terms of designing, you can describe any one of these description levels. All the descriptions will give the same output only. Okay, so next what we have studied is a Boolean equations with respect to basic laws and the operations in terms of Boolean, like operations in terms of Booleans as well as the theorems. Like particularly we have studied commutative law, associative law, and the distributive law, which will give you an advantage, or it will indicate something to change the one expression form into another expression form, or in terms of an operations also. Like another one that we have studied is a De Morgan's theorem, which is very helpful in case of simplification. De Morgan's theorem and duality theorem also will help us to convert the product into an R term or R into an product term. Okay, any doubts? Okay, thank you students. I hope you are understood. ಹೆಂಗಂತದೆ ಸರಿ